right, this is gas laws part 2. We'll start off with another ideal gas law example. So in this example, we're considering a teeny little popcorn kernel, which weighs about 0.13 grams and has a volume of about 0.095 milliliters, containing 0.17 grams of water. We want to use the ideal gas law to calculate the pressure of gaseous water at 100 degrees Celsius when it's confined to the popcorn kernel. And so the heat converts the water to gas, and ultimately that's what pops our little popcorn kernels. So I noticed that I have two masses here, and I'm thinking, well, I know I need moles. I don't know the molar mass of a popcorn kernel. So I'm going to go ahead and say that the thing we're focusing on here is the gaseous water. So I can ignore that 0.13 grams. Instead, the first thing I need to do is turn my 0.017 grams of water into moles so I can use the ideal gas law. Thus, I'm going to just use a tiny baby Stoich table. Molar mass of water, grams to moles. This is a really small amount, and that's what I'm expecting. You can't fit a lot of water into a single popcorn kernel. So we've got 9.43 times 10 to the negative 4 moles of water. Now I can pop that into the ideal gas law. So we're trying to find the pressure. I have the volume. It's given in milliliters, so I need to convert it to liters. So I just divide it by 1,000. So I have 9.5 times 10 to the negative 5 liters. That's equal to my moles of water, 9.43 times 10 to the negative 4 moles. And then I have my constant R, 0.0821 atmosphere liters per mole Kelvin. And then I'm multiplying by my temperature, 373 Kelvin, to get my answer. So I can multiply the right-hand side all together and then divide by the left-hand side, and that should give me the pressure. All right, so there's those, the right-hand side all combined together, and you'll notice that I canceled out my moles and my Kelvin when I multiplied, so now I just have atmosphere liters. And then the pressure is going to end up being 303.98 ATMs. So that's about triple atmospheric pressure on Earth. You guys, stop. My dogs are trying to eat each other right now. Get away. Crazy dogs. Okay. In addition to the ideal gas law, which is very useful, we also have Dalton's law of partial pressures. And the reason Dalton's law of partial pressures is important is that there's not that many cases where we're dealing with one gas in isolation all by itself. The air we breathe is a mixture of gases, and it's just really helpful to be able to think about each gas individually and all the gases as a whole. Like everything else we've talked about, this pretty much depends on the gas being an ideal gas, so that's just the assumption that we're going to be making, continuing to make going forward. Dalton's law of partial pressure is super straightforward. It says that the total pressure is equal to the pressure of each gas in the mixture added together. So if you have one volume for your containers, you have 4 little blue molecules, and they require pressure of 2 to keep the piston at the right height. And then you have the red molecules, and you have 2, 4, 6, 8, 10 of them, and you need 5 piston or little weights to keep that piston at the right height. If you combine and mix the two gases, then you're going to need 7 little weights to keep the piston at the same volume. Right, so we just added our 2 gases together, and so we had to add our 2 weights together to be able to exert the same pressure and keep it at the same volume. So when we write this out, we can note that there's a direct relationship between the partial pressure of a gas and the number of moles of that gas. So if you knew the total pressure and you knew the mole fraction, you can find the partial pressure that each gas contributes. So in this case, what we're looking at is we've got a total of 14 gases gas molecules, whatever, 14 gas molecules, and 4 of them are the blue kind. So if we want to make a mole fraction, we're really just saying, kind of like find a percentage. So I would do the 4 blue ones divided by the total number of 14, and that's going to give me my mole fraction. Then I can multiply that by the total pressure to find the partial pressure, excuse me. Sorry, it's like cloudy and rainy and sleepy. So here's the details of mole fraction. It's the ratio of the number of moles of one component in a mixture to the total number of moles in the mixture. And this applies to everything. It doesn't just apply to gases, it applies to liquids and solids as well. So if you can count the individual moles, you know how many moles you have, you can add them up, you can find the mole fraction. That's always true. So let's apply Dalton's law of partial pressures. A gaseous mixture made from 6 grams of O2, 9 grams of CH4 is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas and what is the total pressure in the vessel? There is about a million ways you can solve this problem, okay? So if what I do doesn't make sense and you're like, why couldn't you just blah, blah, blah? Well, you probably can. You probably can. So give it a shot, see if you get the same answer. I'm going to show you one way to solve it. It's not the only way. It might not be the best way. It's just the way that I do it, okay? So first thing I think is, gosh, grams are useless to me. So I'm going to turn my O2 and my CH4 into moles. That's always a good place to start with a problem. Just turn everything into moles. So grams of oxygen go into moles of oxygen using molar mass, and grams of methane go into moles of methane using its molar mass. And at this point, what I'm going to do, I think, is find the partial pressure of each gas, because I know the volume, I know the moles, I know the gas constant, and I know the temperature. So I can solve for pressure. So I'm going to set that up for oxygen first. So I put in my unknown pressure as variable P, then I have my 15 liters equals the moles of oxygen, 0.1875 moles times the gas constant times 273 Kelvin. I'm going to multiply the right side together, divide the right side by the left side. That gives me 0.28 atmospheres, and that's the partial pressure of my oxygen gas. Do the same thing with the methane, but I just substitute in the methane number of moles, which is 0.5625, and that comes out to be 0.84 atmospheres. So I've answered part of the question, which said, what are the partial pressures of each gas? I've given the partial pressure for each one on this slide. Now the next part, I need the total pressure. Really simple. I can just add the two partial pressures together, 0.28 plus 0.84, 1.12 atmospheres. Okay, one last example and then we're done. We have a flask. It's got a mixture of gases. It's got 2.5 moles of hydrogen, 0.5 moles of oxygen. It's got argon in there, and we don't know how many moles of argon we have. We just know that the partial pressure of argon is 2 atmospheres, and we know that the temperature is 127. So first things first, it says calculate the total pressure in the flask. Well, normally I would just add all my moles together and use Pivner, but I don't know how many moles of argon I have. So what I'm going to do is I'm going to find the partial pressure for just hydrogen gas and oxygen gas, and then I'm going to add the partial pressure of argon at the end. Okay, so it's going to look like this for part A. So the partial pressure of hydrogen and oxygen is 8.2 liters equals 3 moles times the gas constant R times 400, and my 3 moles comes from adding together 2.5 moles of H2 and 0.5 moles of O2 to include both of those in my calculation. So I'm going to go ahead and solve that out. That means there's 12.01 atmospheres contributed by oxygen and hydrogen. And then I can just add the 2 atmospheres contributed by argon, and that gives me a total of 14.01 atmospheres. So that is definitely my total pressure. So I checked off part A. Now I need to find the mole fraction of H2 in the flask. That means I need to figure out the total number of moles in the flask so that I can find that mole fraction. So to do that, I'm going to use my total pressure that I just found and solve for the total number of moles in the flask. So I'm plugging in everything just the same, 14 atmospheres, 0.82 liters equals moles times the gas constant times 400. Solve that out. That means my total moles is 3.5 moles. I just want moles of, I just need the mole fraction for hydrogen. Mole fraction is represented by chi. So I have 2.5 moles of hydrogen divided by the total moles, 3.5 moles, and that gives me a mole fraction of 0.71. Last but not least, we need to find the density. So for the density, it's in grams per liter. So the first thing I think is, gosh, I need to change all this stuff into grams. So I use my moles of hydrogen and the molar mass and find grams of hydrogen. Same thing for oxygen. I know that I have 3.5 total moles of gas, so I can subtract and find out that I only have 0.5 moles of argon, and so that gives me 20 grams of argon. Density is mass divided by volume, and that funny looking squiggle sort of D-like character is delta, lowercase delta, stands for density. So I'm just going to add all the masses together and divide by the volume they occupy, and that gives me a density of 5 grams per liter, right? So you have about 17 practice problems, a couple for each type of example, and that'll be the last thing we do for the gas laws part of this unit. We're going to have one more set of notes in practice. It's going to be about solutions, and we'll be done. Love you guys. I hope that you are taking good care of yourselves and each other. I'll talk to you soon.